Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest, most captivating mysteries ever whispered by physics. The idea that even the emptier space around you may not be empty at all. Instead, it may be humming, quietly, constantly, with a hidden energy that never fully rests. Before we wander into that secret landscape, feel free to dim the lights, let the air grow still around you, and settle into a comfortable breath. If you'd like, imagine yourself drifting in the gentle dark between distant stars, where silence feels almost complete, yet something subtle lingers beneath it, like the faintest vibration. That delicate tremor, woven into the fabric of reality itself, is where our story begins. And as your mind drifts at its own pace, you're welcome to follow along softly. There's no need to hold on to every detail. We'll be here, unfolding the mystery in gentle waves. When you're ready, we'll take our first step into that quiet hum of existence. There's a comforting feeling that comes when you imagine true silence. A room without sound, a night without wind, a distant landscape where everything seems to pause. But even in our most peaceful moments, silence is never perfect. There's always a hint of something lingering. The soft whir of a ceiling fan, the faint drumming of your own heartbeat, the subtle air moving around unseen. And if we look deeper, far deeper than our senses are built to notice, silence becomes an illusion altogether. Because in physics, even the emptiest place imaginable is not empty at all. It trembles with something delicate, something persistent, a kind of universal whisper known as zero-point energy. To begin understanding this strange idea, imagine stripping the universe down to nothing, not just taking away stars and planets, but removing every atom, every molecule, every grain of dust, every glimmer of light. Picture a cosmic room that has been cleaned so thoroughly that not even the tiniest particle remains. You might expect this perfect emptiness to be cold, still, and silent. But the universe has other plans, and nature refuses to sit perfectly still. In the world of quantum physics, the foundations of matter behave more like instruments than solid objects. Every electron, every proton, every particle you've ever encountered behaves as if it's part of a tiny orchestra, always vibrating, shifting, and humming with a rhythm of its own. And even when you take the particles away, those invisible instruments remain. What is left behind is not a void, but a kind of trembling stage made of fields, each capable of vibrating even when no performers stand upon them. These are the quantum fields, and the slight vibrations that remain when everything else is gone are what physicists call the zero-point motion. It's tempting to think of this hum as a minor detail, an odd footnote in the story of physics, but it's far more fundamental than that. The idea comes from one of the core rules of the quantum world. Nothing can ever be perfectly still. If you imagine a spring, even one made of pure light and imagination, you can push it down or pull it up, but even when you try to let it rest at its natural position, it will still jiggle a little. That tiny jiggle is the essence of zero-point energy. It doesn't come from friction or heat or the environment. It is built into existence itself. This comes from a deep principle that says you can never know both where something is and how fast it's moving with absolute precision. If you try to hold both ideas too tightly at once, reality gently pushes back, forcing a little motion into the picture. This means the universe cannot lock anything into perfect stillness. Even at a temperature of absolute zero, which we often imagine as the coldest possible state where all motion ceases, there is still a trace of movement. Not chaotic, not wild, but a soft and persistent trembling. It's like trying to freeze a ripple on a pond. Even if you remove the wind, the fish, and every disturbance, the water itself carries a memory of motion. Its surface never becomes a perfectly smooth sheet. There is always a residue of activity, too subtle for the eye but etched into its nature. The vacuum of space behaves the same way. It carries an imprint, a leftover shiver that cannot be erased. What's astonishing is that this trembling exists everywhere. It doesn't matter where in the universe you look, between stars, inside atoms, in the dark spaces between molecules, even in a patch of empty air right in front of you. The vacuum is always quivering. If you were able to shrink yourself down to scales far smaller than atoms, you might see these ripples moving through nothingness, like the soft pulse of a distant drum. And this trembling is not some abstract mathematical trick. We see its fingerprints woven through reality. The technologies that shape modern life, from magnetic resonance imaging machines in hospitals to the lasers in your phone, depend not only on the existence of quantum rules, but on the fact that the universe's quiet hum is real, measurable, and essential. Without this hidden vibration, matter would collapse into something unrecognizable. The world, as we know it, simply would not exist. Perhaps the most poetic part of this story is that you've lived with this hum for every moment of your life without ever noticing it. The 0-point field is like the background presence of the world, the part that never goes silent, even when everything else has faded. It is the universe's soft heartbeat. As we drift deeper into this idea, we'll explore how this subtle energy shapes the tiniest particles and the largest expanses of space, and how it might even carry the seeds of future technologies that feel almost too wondrous to imagine. But for now, it's enough to know that the quiet around you is not quiet at all. Beneath every second of your life, the universe hums, endlessly, patiently, with a rhythm older than time. There is a comforting idea we often carry with us, the sense that stillness is something absolute. A stone resting on the ground seems motionless. A quiet evening without wind or footsteps feels suspended in time. Even the image of deep space, dark and vast, gives the impression of perfect calm. But the deeper we look, the more this idea dissolves into something softer, more mysterious. Stillness, as we imagine it, is not a natural state of the universe. It is a kind of illusion created by our scale, our senses, and the limits of our everyday experience. To understand why true stillness is impossible, it helps to imagine something familiar, a small object at rest, maybe a pebble resting in your hand. To you, it feels completely still. But if you could shrink yourself down to the scale of atoms within that pebble, the picture would change completely. You would see its inner structure buzzing with motion, atoms vibrating, electrons shimmering in diffuse clouds, and tiny forces pulling and pushing in ways that never quite settle. Even if you tried to freeze this scene by cooling the pebble to the coldest temperature imaginable, its internal landscape would not grow silent. There would still be life inside that quietness, tiny tremors that cannot be taken away. This strange truth comes from one of the gentlest yet most profound principles in quantum physics. It says that nature refuses to let us pin down certain details with perfect clarity. We can describe where something is, or how fast it moves, but not both with absolute exactness. If we try to clamp one quality firmly in place, the other slips away like sand sliding through cupped hands. This delicate balancing act has a quiet consequence. If a particle were to ever stop moving completely, we would know both its position and its motion too perfectly. And the universe, for reasons we are still learning to understand, simply does not allow that. So even when an object is as cold can be, when its temperature sinks toward absolute zero, the point we normally imagine as the end of all motion, a residue of activity remains. It is as if the universe protects a tiny ember of movement, a last whisper of energy that cannot be extinguished. This remaining motion is not chaotic. It is not a restless fidgeting like the agitation caused by heat. It is a quiet, fundamental trembling, much more like the soft vibration of a drawn bowstring that continues long after the music has faded. One of the simplest ways physicists imagine this trembling is through the picture of a tiny spring. Not a spring made of metal, but an abstract spring, one that exists only to help us understand the rhythm of a quantum object. In classical physics, spring can sit perfectly still when no force acts upon it. But in quantum physics, the spring never comes fully to rest. Even in its calmest state, it has a bit of motion left, a bit of energy left. This gentle sway is the 0-point motion, the baseline that nature refuses to go below. Though the idea sounds abstract, it is woven into ordinary reality. Consider something as simple as a molecule of hydrogen, the smallest and lightest of all molecules. At everyday temperatures, it vibrates and rotates in lively ways. But even if scientists cool it to nearly absolute zero, the molecule still wiggles, refusing to freeze. This leftover vibration stems directly from 0-point energy. It is not noise, not friction, but a byproduct of the universe's rule that something can never be perfectly pinned down. Another way to imagine this is to think of a perfectly calm lake. On a windless day, the surface may look like a mirror, smooth and silent. But if you step close enough, or if you wait long enough, you can see tiny ripples moving across the surface, some too small to notice unless the light hits them at just the right angle. These ripples are not caused by wind or fish or falling leaves. They are a natural part of the water's delicate balance. The vacuum of space behaves in a remarkably similar way. Even when everything is removed, when all external influences are stripped away, the surface of reality carries small ripples of motion that cannot be erased. These tiny, unavoidable movements have enormous implications. They mean that the fabric of reality is never rigid or frozen. It is always gently quivering, like the faint vibration of air inside a musical instrument waiting to be played. It is this quiet, universal movement that gives rise to 0-point energy, the soft heartbeat of existence that persists even in the absence of matter and heat. This phenomenon is not just an interesting idea, it is a necessity for the stability of the world. Without the gentle, ever-present trembling built into atoms, many structures that define life and chemistry would simply fall apart. Electrons would collapse inward, molecules would lose their shape, and the rules that govern a matter would unravel. What seems like a tiny detail, the refusal of the universe to be perfectly still, is one of the fundamental reasons reality looks and behaves the way it does. You can think of 0-point energy as a kind of safety margin built into the universe, a quiet cushion that keeps the fabric of things from tearing under its own weight. In a way, the universe hums in order to stay whole. We may not hear this hum with our ears, but its effects echo across everything that exists. As we drift onward, this idea of impossible stillness will become even more significant. For if the universe cannot be perfectly quiet, if every corner of space carries a trace of motion, then emptiness itself becomes a source of possibility. It becomes a reservoir of subtle energy, a stage where invisible dancers move to a rhythm we barely understand. And from this quiet, inevitable trembling, many of the universe's most remarkable mysteries emerge, mysteries we will explore as our journey continues, one soft breath at a time. If you imagine yourself standing on a quiet shoreline watching the ocean in the early morning light, you might feel a sense of calm settle over you. Even when the water appears still, the ocean is never truly at rest. Beneath the surface, countless small motions, currents, tides, and gentle pulses of water move in ways too subtle to notice at first glance. The universe, in its deepest layers, behaves in a remarkably similar way. Even when matter, heat, and light are stripped away, the very foundation of reality continues to ripple with a soft, persistent motion. This is not motion in the ordinary sense. It is not swirling winds or drifting sand. It is something quieter, more fundamental, the trembling of quantum fields. Quantum fields are not objects in the way we normally think of them. You cannot pick them up or see them under a microscope. Instead, they are like invisible blankets stretched across the entire cosmos, filling every corner of space, even places where nothing else exists. Every particle you've ever heard of, electrons, photons, quarks, is simply a tiny vibration in one of these fields. An electron is not a miniature sphere or a speck of matter floating in space. It is the smallest possible ripple in the electron field. Light is a ripple in the electromagnetic field. Everything that exists is a wave in something deeper. To picture these fields in a gentle way, imagine an enormous sheet of fabric stretched tight across a room. Even if nothing touches it, the fabric is not perfectly motionless. Air currents, tiny imperfections, and the tension in the threads keep it quivering softly, continuously. Now imagine that this sheet extends not just across a room, but across the entire universe. That is how a quantum field behaves. Nothing can completely silence it. Its surface always holds a quiet echo of motion. What makes this idea so astonishing is that these tiny ripples are present everywhere, even in places we think of as empty. When you walk through an empty room, you know the air around you is real, even if you cannot see it. When you look at the night sky, you know there are gases and particles between the stars. But quantum fields exist even in the absence of air and particles. They are the true background of reality. The trembling of these fields is the zero-point energy we have been exploring. Each field carries countless ways to vibrate, like the strings of a grand instrument with an infinite number of notes. Scientists sometimes describe these vibrations using modes, softly imagining each mode as a tiny spring capable of bouncing in its own rhythm. In a classical world, you could compress a spring fully until it held no energy at all. But in the quantum world, even when you soften the spring into its quietest possible state, a small amount of motion remains. This motion, repeated across all the modes of all the fields in existence, creates a sea of energy so vast and so subtle that it surrounds us continuously. And yet, despite its richness, this trembling sea is not something we can easily tap into or notice. It is not like electricity running through a wall socket or the warmth of sunlight that you can feel on your skin. Zero-point energy is gentle, almost shy. It hides itself in the cracks of physics, influencing things in ways that are significant but often invisible. We only truly see its presence when we look at the world with extraordinary care, using tools fine enough to reveal the hidden architecture of reality. One such example can be found in the very tools that allow doctors to look inside the human body. The machine known as an MRI scanner, magnetic resonance imaging, relies entirely on the principles of quantum mechanics. Although it does not directly use zero-point energy as a power source, its operation depends on the behavior of atoms and their magnetic properties, which themselves emerge from the world governed by quantum fields. In this sense, every scan, every image, and every moment of insight produced by these machines owes its existence to the quantum rules that also give rise to the universe's quiet trembling. Or consider lasers, which seem almost magical in their precision. A laser beam is a synchronized ripple in the electromagnetic field, a kind of perfectly choreographed dance in which trillions of light waves move in step. This harmony arises only because quantum mechanics shapes how atoms release energy. Without the rules that also give us zero-point motion, lasers would not shine, and much of modern technology would fall silent. So even though the zero-point field feels distant from everyday life, its influence is threaded through the technologies we rely on without second thought. This sea of invisible tremors also helps explain why matter behaves as it does. Without the quiet motion of quantum fields, atoms would collapse inward, unable to maintain their structure. Electrons would fall directly into the nucleus. Chemistry, as we know it, would not exist. The zero-point vibration acts like a built-in cushion, preventing the collapse of the smallest structures of matter. It is as though the universe protects its own architecture with a soft layer of invisible motion. When we widen our imagination a little further, we can feel the weight of this idea. It means the vacuum is not the absence of everything, but the presence of something profound. It is a stage filled with silent performers. It is the background hum of an ever-living world. And if you were to drift out into interstellar space beyond planets and stars, beyond gas and dust, the sea of quantum fields would still surround you. You would be immersed in a subtle ocean, even in the loneliest reaches of the cosmos. This view changes the way we think about emptiness. Instead of imagining a void, we begin to imagine a foundation, an ever-present richness beneath all existence. The universe is not built on emptiness. It is built on this gentle sea of motion, the soft undercurrent that holds everything together. As we continue, we will explore how this sea sometimes reveals itself in experiments that measure the tiniest forces imaginable, and how these small discoveries whisper clues about the deepest nature of reality. For now, let it be enough to know that beneath your quiet breathing, beneath the calm of the night, beneath the stillness of the world, the universe is alive with motion so soft it almost becomes a lullaby. If you sit quietly in a room for long enough, you might begin to notice things you normally overlook. The faint ticking of a clock, the murmur of distant traffic, the soft settling of the walls, sounds that were always there, simply hidden behind your thoughts. In much the same way, when physicists peer deeply into what we call empty space, they begin to notice subtle movements that were always present but too fleeting, too delicate for our ordinary senses to perceive. These motions are not created by particles entering the scene or by anything pushing from the outside. Instead, they arise spontaneously from the restless nature of the vacuum itself. This mysterious restlessness takes the form of what scientists call vacuum fluctuations, tiny, momentary disturbances in the quantum fields that fill all of space. But the word fluctuation can sound too mechanical, too cold. It might be easier and gentler to imagine them as little flickers of activity, like fireflies blinking in and out of view in a dark meadow. Each flicker appears for an instant, dances briefly in the quiet, and disappears again without leaving a permanent trace. These flickers are often described as virtual particles, though that name can be misleading. They are not particles in the way dust or sand or raindrops are particles. They are more like temporary ripples in the fields, allowed to appear for a moment so long as they fade just as quickly. If you could shrink yourself down to the smallest imaginable scales, far beyond molecules, far beyond atoms, and even far beyond the nucleus of the atom, the vacuum would no longer look smooth. It would resemble something alive, flickering with brief bursts of light and shadow. These flashes would be everywhere, arising, fading, arising again, like sparks in a fire constantly being lit and extinguished. This restless choreography is a direct expression of zero-point energy, the baseline motion that cannot be removed from the universe no matter how cold or empty it becomes. At first, this might sound like a poetic exaggeration, but vacuum fluctuations are not merely a theoretical fantasy. They leave measurable footprints. In fact, they influence the behavior of real particles in ways we can detect. Consider the humble hydrogen atom, the simplest structure in all of chemistry, made of just one proton and one electron. If the vacuum were perfectly still, this atom would have a certain well-defined shape, with the electron occupying a set of predictable energy levels. But when scientists look closely, they see a tiny shift in one of these levels, a slight nudge that has no explanation, unless we recognize that the vacuum around the atom is constantly quivering. These fleeting fluctuations tug on the electron ever so slightly, altering its behavior. This tiny shift, discovered decades ago, is one of the first hints that the vacuum is not empty at all. Another gentle example lies in the weak forces that attract molecules to one another, forces so delicate they can be overwhelmed by the brush of a finger or the warmth of the air. Some of these interactions arise directly from the low murmur of the quantum vacuum. When two neutral atoms drift close together, their electrons feel the soft pull and push of virtual flickers in the surrounding fields. The atoms reach toward one another, not because of chemical bonds or magnetic attraction, but because the vacuum between them is restless. It is as though the space around them encourages a quiet closeness, guided by fluctuations that never fully disappear. Perhaps the most striking demonstration of vacuum fluctuations emerges when we create an environment where they can be shaped. Imagine placing two perfectly flat, uncharged metal plates extremely close to one another, so close that the gap between them is only a few atoms wide. You would expect nothing unusual to happen. No forces, no attraction, no mysterious movements. And yet something remarkable emerges. The vacuum between the plates cannot fluctuate in the same way as the vacuum outside, because the space between them is confined, restricted, limited in how it can ripple. The result is a tiny imbalance, a small pressure coming from the outside vacuum being allowed to quiver more freely than the inside. This imbalance gently presses the plates together, creating a force that can be measured in the lab. This effect, known as the Casimir force, is one of the clearest pieces of evidence that the vacuum is alive with activity. And the beauty of it lies in its simplicity. No exotic materials are required, no complicated machinery, only the presence of empty space shaped by simple boundaries. By adjusting the geometry of the plates, changing their distance, their shape, or their orientation, we can tune the behavior of the fluctuations, almost as if we were learning to lightly touch the invisible fabric of the vacuum and watch it respond. Modern experiments have taken this idea even further. Scientists have placed tiny spheres near flat surfaces, or used delicate materials like graphene, sheets of carbon only one atom thick, to explore how vacuum fluctuations behave on the smaller scales. They have even discovered conditions where the Casimir force becomes repulsive, pushing objects apart instead of drawing them together. All of this arises from nothing more than the quiet, persistent flickering of virtual particles. These fluctuations also play a role in the way charged particles interact with one another. Surround a charged particle with a cloud of virtual particles, and you subtly change the strength of its electric field. In this way, the vacuum can insulate, distort, or reshape the forces that govern matter. It is like adding a fine mist around a glowing lantern. The light still shines, but its reach is softened and its edges grow hazy. Taken together, these effects remind us that the vacuum is not truly empty, but is more like a canvas of possibilities, constantly rearranging itself. Its fluctuations might be tiny, but their influence stretches across the structure of matter. Without them, atoms would behave differently. Molecules would lose their familiar bonds, and the physical world would feel strange and unfamiliar. As we move further into our quiet journey tonight, we'll see that these small flickers of activity do more than shape the tiny realm of particles. They also whisper secrets about the cosmos on its larger scales. From the tiniest tug between atoms to the stretching of the universe itself, the vacuum's dance of subtle motion reaches into every corner of reality. And in this dance we find hints of an energy that is both humble and profound, a reminder that the universe's quietest places are often the most alive. Imagine placing your palms close together without letting them touch. At first glance, nothing seems to happen. There's simply a thin slice of air between them, transparent and unremarkable. Yet, if your hands were made of perfectly smooth metal plates and they were positioned unimaginably close, so close that only a few dozen atoms could fit in the gap between them, the empty space between your palms would begin to behave strangely. Something gentle but persistent would push them together, as though an invisible pressure were nudging from the outside. This subtle force, whispered into existence by the quiet trembling of the vacuum, is known as the Casimir effect, and it stands as one of the clearest pieces of evidence that the emptiness around us is anything but empty. To understand why this happens, it helps to imagine the vacuum as a restless surface, alive with tiny ripples. These ripples correspond to the smallest possible vibrations of the quantum fields that fill space. When nothing gets in their way, they can wiggle and sway freely, producing different rhythms, some long and slow, others quick and sharp. But when you introduce boundaries, such as two closely placed metal plates, you limit the ways these invisible waves can move. Between the plates, only certain subtle modes of vibration are allowed, while outside them, the vacuum continues its full dance, uninterrupted. You can think of it like trying to pluck a guitar string while holding your fingers very close together along its length. Only certain tones can resonate, others are silenced. In the vacuum, the tones that are silenced are the modes of fluctuation that simply cannot fit between the plates. This creates an imbalance. Outside the plates, the vacuum has more freedom to tremble. Inside, it has less. The result is that the plates feel a small pressure from the outside, nudging them closer. This is the Casimir force, a quiet push created not by air or magnetism, but by the structure of the vacuum itself. This idea might seem whimsical, almost like a metaphor, but it is measurable in the lab with exquisite precision. In the late 1990s, scientists began performing highly sensitive experiments to confirm the Casimir effect. They used polished metal plates and tiny measurement devices capable of detecting forces far weaker than the weight of a single grain of dust. And astonishingly, the force appeared exactly as predicted. Even more surprising, it changed in exactly the way theory anticipated. As the plates were brought closer together, the force grew stronger, because the vacuum between them became even more restricted in how it could tremble. One of the most elegant experiments involved bringing a small metallic sphere near a flat metal surface. This setup made it easier to control the distance with extraordinary precision. As the gap narrowed, the sphere was gently drawn toward the surface by a whisper of force. Nothing else could explain this pull. Not static electricity, not magnetism, not thermal currents. Only the restless vacuum, reshaped by the geometry of the objects, could account for the effect. Modern versions of these experiments use materials like graphene, a sheet of carbon only one atom thick. Because graphene is so light and so responsive, it can reveal tiny variations in the Casimir force more clearly than heavier materials. Scientists have even created conditions in which the Casimir force becomes repulsive rather than attractive, by carefully arranging the shapes and materials involved. This reversal doesn't violate any laws of physics, it simply reflects the fact that the vacuum behaves like a complex instrument, one whose notes depend sensitively on the shape and tension of its strings. If this sounds like we're describing a kind of invisible pressure, that's because, in a way, we are. But it is not pressure from air. nor pressure from any kind of physical substance. Instead, it is a pressure created by the difference in the vacuum's ability to vibrate in different regions. Some physicists describe it as the vacuum trying to regain its freedom. But even that is simply a soft metaphor for a deeper truth. The vacuum's energy depends on its shape. This subtle dependence connects the Casimir effect to other quiet phenomena in nature. In the world of atoms, a similar principle influences how electrons move around nuclei. The vacuum around an atom is filled with small momentary flickers, virtual particles that appear and disappear in a shimmer of activity. These flickers slightly shift the energy of the atom, causing tiny deviations from what a perfectly still vacuum would predict. One such shift, known as the Lamb shift, was discovered long before the Casimir effect was measured, but both phenomena point to the same idea. The vacuum is dynamic, structured, and deeply woven into the workings of matter. You can imagine these fluctuations like the faint rustle of leaves in a forest. Even when there is no obvious wind, the leaves still move, stirred by currents too subtle for you to feel. In the vacuum, the wind is the constant dance of quantum fields. And when boundaries like the metal plates interrupt this dance, the surrounding space responds with a gentle push or pull. It's remarkable to realize that something so abstract, the shape of empty space, can produce a force that acts on actual objects. This suggests that the vacuum is not a passive background, but a participant in the universe's behavior. It interacts with matter, it responds to geometry, it molds itself around the structures placed within it, and in return it nudges those structures in delicate, measurable ways. This understanding has important implications for modern technology. In the world of tiny machines, microdevices and nanodevices with moving parts only a few atoms thick, the Casimir force can become strong enough to matter. Engineers must account for it, lest moving parts stick together unexpectedly. In a way, our growing ability to build smaller and smaller machines forces us to confront and work with the vacuum's subtle behavior. We are beginning to design with emptiness in mind. All of this invites a quiet realization. The vacuum is not a void to be ignored, but a medium with texture and personality. It can be shaped, confined, and influenced. And as we continue to learn more about it, we may find new ways to interact with this subtle ocean of trembling fields. For now, though, it is enough to know that the emptiness between two metal plates carries a hidden richness, and that by holding that emptiness in your hands, you can feel the universe whisper back. If you hold a small object in your hand, a smooth pebble from the beach perhaps, or a polished piece of metal, it feels solid, still and dependable. You might rotate it between your fingers, noticing its weight and texture, the way it resists pressure in a calm, familiar way. But beneath that sense of stability lies a world that is anything but still. Every atom inside that pebble, and every atom inside you, is gently vibrating, not because of heat or motion, but because the universe refuses to let anything rest completely. These soft vibrations are not the chaotic jostling of molecules at warm temperatures. They are quieter, more fundamental. They arise from the zero-point motion we've been exploring, a hum so subtle that it whispers beneath everything we know. One of the most striking examples of this hidden motion can be found in helium, a simple and common gas that behaves in an extraordinary way when cooled. Imagine lowering the temperature of helium to nearly absolute zero, the point where, in our everyday intuition, everything ought to freeze into a rigid crystal. Most substances behave exactly as we expect. Their atoms lose energy, fall into a tidy arrangement, and become solid. But helium resists this fate. Even when it's colder than any natural place in the universe, helium refuses to freeze. Instead, it remains a liquid, flowing and swirling with remarkable grace. This defiance of freezing is not due to impurities or external agitation. Rather, it is the result of zero-point motion. The atoms of helium are so light, so delicately bound, that even the faint trembling imposed by the universe's foundational rules prevents them from locking into a solid structure. Helium is, in a sense, kept fluid by the quiet hum of the vacuum. If we look around our own lives, we find similar stories woven into the materials we depend on. The chemical bonds that hold molecules together, bonds that give structure to water, wood, air, and even the cells in your body, are influenced by the quantum vacuum. Consider the humble water molecule. Its familiar shape, two hydrogen atoms clinging to an oxygen atom like children holding a parent's hands, depends on a balance of forces partly shaped by subtle vacuum fluctuations. If these fluctuations did not exist, or if they behaved differently, water might not behave as we know it. Its ability to expand when frozen, its remarkable surface tension, its role as the universal solvent, all the features that make water essential to life, would shift, perhaps in ways that would make our world unrecognizable. Another example lies in the delicate forces that allow geckos to climb walls and walk across ceilings. Geckos do not possess magical adhesive pads or tiny claws that hook into microscopic imperfections. Instead, their feet are covered with millions of tiny hairs that come into extremely close contact with surfaces. At these distances, the vacuum itself begins to play a role. Small, attractive forces known as van der Waals interactions, born from the fleeting dance of electrons and vacuum fluctuations, give geckos their astonishing grip. These forces are gentle enough that you can easily peel a piece of tape, yet strong enough to let a small animal defy gravity. It is the vacuum, trembling quietly between surfaces, that provides the final touch of adhesion. Even the air we breathe is touched by zero-point energy. Consider nitrogen and oxygen molecules floating freely, bumping into each other, sometimes forming temporary arrangements and then drifting apart again. These gentle dances are influenced by the same subtle attractions that guide geckos, rooted in the vacuum's momentary flickers. Without these weak forces, gases would not behave the way they do. Their densities, diffusion rates, and even the way they condense into liquids would change. The quiet vacuum contributes to the stability and structure of the entire atmosphere. If we zoom into the realm of electronics, we find another place where zero-point energy leaves its soft fingerprints. Modern electronics rely on the precise behavior of electrons moving through materials. These electrons do not move like tiny marbles rolling through tubes. They move as waves, shifting and overlapping in patterns guided by the underlying quantum fields. The trembling of these fields nudges the electrons into particular arrangements, influencing how well a material conducts electricity. In some materials, this interplay allows electrons to move so freely that they encounter almost no resistance. These materials, known as superconductors, pass electric current without losing energy as heat. Their behavior arises from a delicate balance of quantum vibrations, an interplay between the electrons and the lattice of atoms around them, both influenced by the ever-present hum of zero-point motion. You might think superconductors belong only in advanced laboratories, but their behavior hints at a deeper truth. Even in familiar metals like copper and aluminum, the flow of electric current depends on subtle quantum interactions that are shaped by these hidden tremors of the vacuum. Every time you turn on a light or charge a device, you're indirectly relying on the quiet structure of zero-point energy to guide electrons along their path. The magnetic fields we use in medicine to peer inside the body also rely on these principles. An MRI machine works by aligning the spins of hydrogen atoms, tiny quantum magnets that respond to powerful magnetic fields. These spins are not fixed or rigid, They quiver, precess, and respond to their environment in ways shaped by quantum motion. Even at temperatures near absolute zero, these atomic magnets would never be perfectly still. Their orientation shifts slightly due to the same foundational rules that govern zero-point energy. Without this responsiveness, the MRI technique would not be possible. In a strange and beautiful way, these machines work because the atoms inside us listen to the whispers of the vacuum. In the world of chemistry, the stability of molecules depends on how electrons distribute themselves around nuclei. These electrons exist not as tiny balls, but as diffuse clouds, always vibrating in subtle ways. These vibrations influence how tightly atoms bind to one another, how molecules bend, how they twist, how they respond to heat and light. All of these properties ultimately depend on the gentle, ever-present motion built into the universe. Without zero-point energy, molecules would collapse inward, electrons would fall directly into nuclei, and chemistry would lose its complexity. The world would be far simpler and far less capable of supporting life. When you consider all these examples together, a picture begins to form. Zero-point energy is not a rare or exotic phenomenon limited to the depths of physics laboratories. It is a quiet partner in almost everything around us. It keeps helium from freezing, allows geckos to climb, shapes the behavior of water, influences chemical bonds, and ensures the stability of atoms. It helps electronics function and enables advanced medical imaging. It is present in every breath we take, every step we walk, and every moment we live. As we continue this journey, we'll begin to see how this soft foundation stretches beyond the scale of atoms and molecules, touching the vastness of the cosmos. The same trembling that shapes the smallest particles might also influence the expansion of the universe itself. For now, let this idea settle gently. The vacuum's quiet touch is everywhere, shaping both the tiny and the immense like a faint melody that moves through everything, even when we cannot hear it. There is a quiet kind of awe that comes from looking up at the night sky. The stars feel impossibly distant, like tiny lanterns pinned to an endless backdrop. Between them stretches a vast darkness that seems empty, spacious, and almost soothing in its silence. But this darkness, the empty space we imagine as nothingness, is far from weightless. In fact, it may be one of the heaviest, most influential elements in the entire universe. To understand how, we need to shift our perspective from the small, familiar world of atoms to the enormous realm of galaxies and expanding space. For most of human history, people assumed that space was simply the stage on which everything else moved. The actors, planets, stars, comets, took the spotlight, while space itself played the role of a quiet, invisible backdrop. But when Albert Einstein developed his theory of gravity, he transformed this understanding completely. Instead of treating space as an empty container, he imagined it as something alive, a fabric that can bend, stretch, curve, and respond to the presence of energy. In this view, gravity is not a mysterious pulling force. It is simply the way objects move through this flexible fabric. A planet circles a star not because the star tugs on it, but because the planet is following the curved shape of the space around the star. This new picture raises a gentle but profound question. If gravity comes from the way space bends in response to energy, then what happens when space is filled with a subtle, ever-present energy like the zero-point motion we've been exploring? Even though this energy is quiet, almost like a background hum, it still counts. It still presses into the fabric of the universe, and the fabric responds. Imagine stretching a sheet of rubber between four posts. If you place nothing on the sheet, it remains flat. But if you sprinkle tiny grains of sand on it, grains so light they barely have weight, the the sheet will still shift ever so slightly. It may sag in places or tighten in others. The effect is gentle, almost imperceptible, but it is real. 0-point energy is like those grains of sand. It is not the dramatic mass of a star or planet, but it is present everywhere, woven into the emptiness we once thought was still. Einstein introduced a term into his equations to describe this quiet influence. He called it the cosmological constant, though in simple language we can think of it as the natural pressure or tension of empty space. At first he included it reluctantly, as a mathematical tool to create a stable universe in theory, a universe that neither expanded nor contracted. Later he removed it, believing it unnecessary. And then, decades after Einstein's passing, astronomers discovered something strange. The expansion of the universe was speeding up. Galaxies weren't just drifting apart, they were accelerating away from each other, as if pushed by a gentle, persistent force coming from the vacuum itself. Scientists now call this gentle push dark energy, though the term is more poetic than explanatory. It does not mean darkness in the usual sense. Rather, it refers to an energy we do not yet fully understand. What we do know is that it behaves very much like the soft, uniform pressure Einstein once tried to describe, the natural tension of space itself. And when physicists calculate the way such a tension affects the universe, they find that it has a kind of weight, an influence on the large-scale structure of everything. To imagine this weight, picture a balloon being inflated. At first, the rubber expands slowly, then more quickly as the pressure inside grows. Now imagine a similar pressure spread evenly throughout the entire universe, not coming from inside a balloon, but from the fabric of space itself. This pressure does not push in one direction or another. Instead, it stretches everything outward, like a gentle tide drawing galaxies apart. And because this pressure is present everywhere, its influence becomes dominant over enormous distances. The idea that empty space has weight may sound contradictory. After all, we usually think of weight as something associated with matter, with solid objects that take up room and resist being lifted. But in Einstein's framework, anything that carries energy affects the curvature of space. Light, although it has no mass in the ordinary sense, can bend the path of objects. Heat can influence the geometry of space around it, and the quiet energy of the vacuum, 0-point motion, also contributes, adding to the universe's overall structure even though it cannot be seen or held. One of the most astonishing aspects of this idea is how small the effect feels locally, and yet how powerful it becomes on cosmic scales. Here on Earth, the influence of 0-point energy is dwarfed by gravity, by the warmth of the sun, by the mass of the planet beneath our feet. It is too subtle to feel. But between galaxies, where the distances are measured in light years and the spaces between stars stretch unimaginably far, this small, steady pressure becomes noticeable. It is like a soft breeze that becomes strong only when there is nothing to block it. And because 0-point energy is woven into the vacuum everywhere, its influence is everywhere. Every patch of space has this quiet tension, this delicate weight that shapes the fate of galaxies. This means that the most dominant force in the universe today is not the explosive heat of stars or the swirling gravity of black holes, but the humble, persistent energy of the vacuum, the same trembling we encountered in the smallest motions of atoms. This connection between the tiny and the enormous is one of the great wonders of modern physics. The same rule that prevents an electron from sitting absolutely still also plays a part in the way the cosmos expands. The same background hum that keeps helium from freezing also shapes the structure of galaxy clusters. It is as though the universe is built on a single melody, played across a range so wide that its notes span from the smallest particles to the farthest reaches of space. Of course, this understanding is still incomplete. Scientists do not yet know exactly how zero-point energy contributes to the accelerated expansion of the universe. They do not know whether dark energy is precisely the vacuum's quiet tension, or something even deeper, shimmering beneath the surface of the cosmos. But what is clear is that empty space is not an absence. It is a presence, gentle and profound, holding a kind of weight that shapes everything we see. As we drift onward, this insight will lead us to an even more startling mystery: the mismatch between what quantum theory suggests this vacuum energy should be and what astronomers actually observe. The gap between these two views is so vast, so striking, that it has been called the most embarrassing problem in physics, and it arises not from failure, but from the remarkable precision of our theories. In the next part of our quiet journey, we'll explore this tension gently, like listening to two distant notes that should harmonize but instead create a strange, haunting chord. When you listen to a piece of music, there's a certain pleasure in noticing how the instruments blend together. A piano chord, the soft breath of a flute, the quiet thrum of a bass. Each sound complements the others in a way that feels natural and whole. But sometimes, if just one note is out of place even slightly, the entire harmony shifts. A subtle dissonance creeps in. Something delicate becomes unsettling. In physics, a similar discord exists between two of our most successful theories. Both play their parts beautifully on their own, but when brought together, they refuse to harmonize, and the disagreement arises from a single, surprising number: the amount of energy we think the vacuum should contain versus the amount we actually observe. To understand this mismatch, imagine sitting at a table and trying to estimate how many grains of sand are in a small jar. You might guess 1,000, perhaps a few thousand. Now imagine that someone later tells you the actual number is roughly equal to all the grains of sand on all the beaches on Earth, and then multiplied again and again until the number becomes so absurdly large it barely fits in your mind. This is the kind of difference physicists face when comparing the predictions of quantum theory to the behavior of the universe. In the world of quantum fields, as we've seen, the vacuum is not silent but filled with tiny tremors, zero-point motions that exist even in perfect cold. If you take these motions seriously and imagine adding up the energy of each tiny vibration across all possible wavelengths, the total becomes enormous. The calculations suggest that even the smallest volume of empty space, something as tiny as the space inside a raindrop, should contain enough energy to outshine entire galaxies. Of course, this energy is not directly visible. It does not burst into light or heat. It remains hidden beneath the surface, folded into the vacuum's quiet structure. Still, its theoretical magnitude is staggering. Now shift from the tiny scale to the largest possible one, the cosmos itself. Astronomers, observing the expansion of the universe, can estimate how much vacuum energy is actually present. What they measure is surprisingly small. The vacuum does appear to have a gentle pressure, one that pushes galaxies apart, but its strength corresponds to an energy density that is incredibly modest. Not enormous, not explosive, but subtle, like a thin veil being stretched slowly over time. Here lies the tension. Quantum theory predicts an energy density for the vacuum that is unbelievably large. Observations in cosmology suggest a value that is unbelievably small. The difference between these two numbers is so extreme that it has become almost legendary. If you try to express the mismatch in familiar terms, it would be like expecting the entire ocean to pour from a drinking straw, but discovering instead a single drop. Or like predicting the Earth will weigh as much as the Sun, and finding that it barely weighs more than a feather. This mismatch is not by a factor of 2 or 10 or even 1,000. it is by a factor so large that we can only describe it in phrases 100 powers of 10, a 1 followed by an almost unimaginable number of zeros. Many scientists refer to it, half jokingly and half seriously, as the most embarrassing problem in theoretical physics. This isn't a mistake made because the theories are sloppy. On the contrary, both of the theories involved are among the most precise frameworks ever created. Quantum field theory, which predicts the enormous energy, has been tested to astonishing accuracy. Some of its predictions match experiment to more than a dozen decimal places. And the theory of gravity, shaped by Einstein's understanding of space and time, predicts the large-scale behavior of the universe with stunning reliability. The issue is not that either theory is wrong on its own, it is that we have not yet found the thread that connects them, the quiet harmony that lets them play together without discord. Physicists have explored many possibilities. One idea is that the enormous energy predicted by quantum theory is cancelled out almost perfectly by some other effect, a kind of cosmic balancing act. Imagine two nearly equal weights placed on opposite sides of a scale. If they match perfectly, the scale remains level. But if even the slightest mismatch exists, the scale will tilt. In this analogy, the universe is the scale, and the tiny tilt we observe, the gentle acceleration of cosmic expansion, suggests that the cancellation is not perfect. Something remains, a leftover, a whisper of the energy the vacuum might contain. Another possibility is that our picture of quantum fields is incomplete, especially at extremely short distances. When physicists estimate the vacuum energy by adding up all possible vibrations, the result depends on including wavelengths far smaller than anything we could ever detect, lengths so tiny that even the idea of space becomes blurry. Perhaps the universe has a natural cutoff, a smallest possible scale, where the fabric of space stops behaving like a smooth surface and becomes something more granular. If such a cutoff exists, it would dramatically lower the predicted vacuum energy, bringing theory and observation closer together. But for now, this idea remains a gentle speculation. Some researchers suggest that the vacuum energy might change over time. Instead of being fixed, it could evolve as the universe expands, like a lantern that slowly dims as it burns. In this view, the mismatch arises not from a single error, but from the fact that the vacuum today is different from the vacuum in the distant past. Yet this idea introduces new questions. What guides the change? How does it unfold? And why does the vacuum have the value it does right now? There are also more radical possibilities. Perhaps gravity does not respond to vacuum energy in the way we expect. Perhaps the vacuum's enormous theoretical energy is real but hidden, woven into spacetime in a way that does not influence expansion, the way other forms of energy do. This would require rewriting some of the deepest rules of physics, not discarding them, but extending them in ways we do not yet fully understand. At times, these ideas feel almost like listening to a melody played by two instruments, one playing too loudly, the other too softly. We know the tune is beautiful, but we cannot yet merge the notes into a perfect harmony. This dissonance is not a failure, though. It is an invitation, an opening, a reminder that even in the areas where our theories shine brightest, mysteries remain. And perhaps there is something poetic in this tension. The quietest places in the universe, the spaces between galaxies, hold a secret that our most advanced mathematics is still struggling to articulate. The smallest whisper of energy, spread across the vastness of space, might hold the key to understanding why the universe accelerates, why it expands the way it does, and how the grand forces of nature connect. As we drift deeper into this journey, we'll explore the delicate thread linking the quantum world to the cosmos. We'll see how the vacuum, restless and trembling at the smallest scales, may also stretch and breathe on the largest ones. For now, let this dissonance settle gently in the mind, not as a puzzle to solve tonight, but as a reminder of how much wonder still lies ahead. If you were to hold a single thread between your fingertips, something delicate, almost weightless, you might notice how easily it sways with the faintest movement of air. The thread is small, almost insignificant, yet it connects your two hands, binding them through something nearly invisible. In the same way, there is a fragile connection running through the heart of physics, a thread stretched between two extraordinary worlds. On one side lies the quantum realm, a place of trembling fields and fleeting particles, where zero-point energy hums softly beneath everything. On the other side lies the cosmic realm, vast and silent, where galaxies drift apart through oceans of darkness. And though these two realms seem impossibly far apart in scale, there is a sense that they belong to the same tapestry. Somewhere between them, something subtle binds their stories. As we explore that connection, it can help to imagine the quantum world not as a separate place, but as the foundation on which the universe is built. Everything we see, from the glow of a distant star to the quiet breath of a sleeping person, arises from tiny interactions happening at scales far smaller than the eye can perceive. If quantum fields are the threads, then the universe we walk through is the fabric they weave together. Each trembling mode, each whisper of zero-point motion adds to the overall texture of existence. This idea becomes especially powerful when we turn our attention to the cosmos. For decades, scientists have measured how galaxies move, how cosmic structures form, and how space itself expands. Again and again, they discover signs that the vacuum, this seemingly empty backdrop, plays a role in shaping the universe. The quiet pressure we discussed in the previous session, the one responsible for accelerating cosmic expansion, is not a separate ingredient added on top of quantum mechanics. It is part of the same story, the story of a vacuum filled with gentle motion. One of the ideas that bridges the scales comes from viewing the vacuum as something that is not fixed, but malleable, changing as conditions change. Just as a blanket pulled tighter softens into different folds, or a sheet of paper held at an angle catches light differently, the vacuum might respond to the expansion of the universe by adjusting its own energy. Some scientists explore this possibility through what they call running vacuum models, which imagine vacuum energy slowly evolving as the cosmos stretches. Instead of being a constant presence, its influence might change gradually over eons, softly, almost imperceptibly, but enough to shape cosmic history. Another delicate link between the small and the large comes from the idea of vacuum condensates. In simple terms, these are arrangements of quantum fields that settle into particular patterns, like ripples freezing into a gentle repeating wave. These patterns play roles in the behavior of particles, but they may also contribute subtle energy densities to the universe as a whole. If you picture the vacuum as a pond, and each condensate as a thin layer of gentle frost forming on its surface, then the combined effect of many such layers could help determine the overall mood of the vacuum, its pressure, its influence, and its cosmic weight. There are even theories that suggest gravity itself might emerge from the collective behavior of quantum fields. This idea is as intricate as it is beautiful. Instead of being a fundamental force, gravity may arise the way patterns arise in crowds or melodies arise in song. Countless tiny quantum interactions might, through their combined behavior, give rise to the large-scale bending of space and time. One early idea along these lines was proposed by a physicist who imagined that space-time's curvature might be the result of quantum fields resisting distortion. In this picture, gravity becomes a kind of elastic response to the movement and energy within the quantum vacuum. Even though these ideas vary in detail, they share a common theme. The universe is unified by a single underlying fabric, and the vacuum sits at the heart of that unity. Zero-point energy, which affects the smallest interactions between atoms, may also whisper its influence across billions of light years. This continuity does not suggest that small effects control the universe in a direct way, nor that cosmic expansion springs entirely from quantum vibrations. Instead, it hints at something more subtle, the same rules, the same principles, woven into different scales of reality. Imagine an enormous tapestry with patterns that repeat at different sizes. Up close, you might see tiny threads forming loops and swirls. Stepping back, you might find similar patterns echoed in the larger design. The relation between the quantum vacuum and the cosmic vacuum is something like this. We see the faint trembling of fields at the smallest scales, and then, at the larger scales, we see the universe respond to a quiet pressure that feels like the echo of those same tremors. Of course, the connection is not simple. The mismatch we explored earlier, the dissonance between theoretical and observed vacuum energy, remains unresolved. It is like hearing a faint harmony in a song, but not quite knowing which instruments produce it. Yet the very existence of such a mismatch suggests that a deeper link is waiting to be uncovered. The vacuum's influence is real. It shapes both atoms and galaxies. But we have not yet found the perfect bridge between the two perspectives. Sometimes, in science, the absence of a complete answer is not a stumbling block but an invitation. It invites us to look more closely, to consider ideas that fall outside our usual boundaries, and to remember that the universe often reveals its truths in gentle, gradual ways. The vacuum, with its quiet hum, may contain clues not only to particle physics, but also to cosmic evolution. And by listening more carefully, we may someday understand how these scales fit together, like notes in a haunting melody played across the entire cosmos. As we drift forward, our journey will turn from the cosmic to the imaginative. We'll begin to explore what might happen if we could interact with this vacuum energy directly, not merely observe it, but perhaps in some distant future shape or draw from it. Such thoughts belong as much to dreams as to theory, and yet they open a door to possibilities both wondrous and humbling. Before we wander through those possibilities, allow the idea to settle. The universe's smallest tremors may be tied to its grandest motions, linked like a thread running through the fabric of everything. There's a certain kind of dream that often appears when humans stand at the edge of a great mystery. You can feel it whenever a new discovery hints at something larger, an uncharted territory where imagination begins to stretch its wings. Zero-point energy is one of those places. The moment people hear that empty space contains a quiet, ever-present tremble, a natural question arises. If the vacuum is filled with subtle energy, could we ever use it? Could we reach into the fabric of reality and draw something out? It is a question that invites both wonder and caution, curiosity and humility. And although we cannot answer it with a simple yes or no, we can explore the dream gently, the way one might explore the shape of a cloud drifting overhead. To begin this thought experiment, imagine standing at the edge of the ocean. Waves roll in, rise, fall, and retreat. They are filled with motion, constant and tireless. If you scoop a cup of water, you find movement inside it, but you don't capture the ocean's entire dance. You only hold a tiny fragment, one piece of the larger rhythm. The ocean continues to move without noticing your attempt. Zero-point energy is similar. It is everywhere, woven into the vacuum itself, but its motion is not something you can easily collect or bottle. Trying to tap into it directly is like trying to scoop the rhythm of waves rather than the water itself. Still, the dream persists. Over the years, various proposals have emerged, some bold, some hopeful, and some more imagination than science. These ideas often begin with a beautiful intuition, that if the vacuum carries energy at its quietest level, perhaps there is a way to nudge it, guide it, or coax a small amount of that energy into a usable form. It is not an unreasonable hope. Nature has surprised us many times before. The atom, once thought indivisible, revealed a vast reservoir of energy. The sun, once understood only as a burning fire, turned out to shine because of the fusion of tiny nuclei. If the vacuum holds energy, perhaps there is a story waiting to be discovered. But as gentle as this dream is, it must be approached with clarity. Many early proposals for vacuum energy extraction misunderstood how the quantum world works. They imagined the vacuum as a kind of hidden fuel tank, full of energy waiting to be drained. But the vacuum's energy is not stored the way fuel is stored in a container. It is more like the tension in a stretched string. You cannot simply relax one part of the string and expect to harvest the tension as usable energy. The vacuum's trembling is a baseline, the lowest possible level allowed by the laws of physics. Anything below that baseline would violate the deep rules that keep nature consistent. So the challenge is not that we lack tools to reach the vacuum. The challenge is that the vacuum has no lower place to fall. You cannot extract energy from the quietest possible state without changing the meaning of quietest. The vacuum already sits at the universe's foundation, as calm can be while still respecting quantum uncertainty. Some of the fringe ideas over the decades, devices claiming to produce limitless energy from empty space, or engines promising to run without fuel, stem from attempting to treat zero-point energy like a reservoir waiting to be drained. In most cases, these devices misinterpret tiny electrical effects, random vibrations, or the natural noise of sensitive equipment. Scientists have learned to recognize these misunderstandings, and the field has accumulated many lessons about how easy it is to mistake the vacuum's quiet hum for something tangible and extractable. Yet if we shift our attention away from extraction and toward interaction, a more promising picture begins to emerge. Scientists have discovered that although we cannot scoop vacuum energy the way we scoop water, we can influence the way the vacuum behaves. We saw this earlier with the Casimir effect. By adjusting the distance between two plates, we reshape the vacuum's possible vibrations. In a way, we tune the vacuum's music, changing which notes can play and which cannot. This tuning does not give us energy in the ordinary sense, but it reveals that the vacuum can respond to boundaries, shapes, and geometry. There is an elegance in this. Instead of trying to overpower the vacuum, we learn to dance with it, to guide its subtle responses, not force them. Modern research in quantum field manipulation explores this idea. At extremely small scales, scientists can create environments where the vacuum behaves differently. Nano-engineered surfaces, tiny cavities, and delicate electromagnetic structures can create regions where the vacuum's fluctuations shift in measurable ways. These experiments do not extract energy, but they demonstrate control. They show that the vacuum is not a featureless emptiness, but something with texture, something we can shape gently. It is tempting to imagine where this kind of control might lead in the distant future. Perhaps one day, we will design materials that respond to the vacuum the way sails respond to wind, structures that guide the trembling of fields in useful ways. Perhaps we'll learn how to encourage certain modes of the vacuum to amplify or silence each other, much like the strings of a violin resonate in harmony. Or perhaps we will discover that the vacuum, when shaped in just the right way, interacts with matter in ways we have not yet imagined. But even as we entertain these thoughts, we must keep our feet on steady ground. The dream of tapping vacuum energy directly remains beyond our reach, and the universe seems to whisper gently that some boundaries are not meant to be crossed by force. The vacuum's quiet hum is not a hidden generator. It is part of the universe's structure, a subtle balance that holds reality together. To pull energy from it would require rewriting rules that shape everything from atoms to galaxies. Still, dreaming is not forbidden. In science, imagination is often the first step toward understanding. What begins as a thought experiment can lead to new questions, new tools, new discoveries. The dream of zero-point energy extraction may remain a dream for now, but the journey of understanding the vacuum continues. And perhaps, in the soft distance of future centuries, we will learn how to interact with this trembling foundation in ways that today's scientists can only describe in gentle metaphors. For now, we hold the dream lightly. Not as a promise, not as a plan, but as a curiosity carried forward with humility. The vacuum hums softly and endlessly, and we are only beginning to understand its symphony. There is a moment in every long scientific journey when wonder must sit beside realism, where imagination looks toward the horizon and understanding gently reminds us of the ground beneath our feet. The dream of tapping the vacuum is beautiful, but when we try to imagine building something real, something physical, something that could sit on a table or power a home, we quickly enter a landscape filled with quiet but formidable challenges. These challenges are not walls meant to stop us, but signposts reminding us how subtle, delicate, and deeply woven the vacuum truly is. To begin, grasping these challenges, imagine trying to lift yourself off the ground by pulling on your own shoelaces. No matter how strong you are, you cannot rise. Your effort simply redirects force within the same system. You pull up, the shoes pull down, and you remain rooted in place. This is similar to what happens when one tries to extract usable energy from zero-point motion. The vacuum's trembling is the baseline of nature. It is not an extra layer sitting on top of reality. It is reality's foundation. Trying to drain it for power is like attempting to pull energy out of the universe's quietest possible state. There is nowhere lower for the vacuum to fall, just as there is nowhere for you to rise when all you are holding is your own shoelaces. Another barrier comes from the way the vacuum distributes its motion. Zero-point energy is not concentrated in one spot, the way electricity can pool in a battery, or heat can gather in a flame. Instead, it is evenly spread throughout all of space, uniform, constant, and extremely stable. This uniformity makes extraction far more difficult than it sounds. If all the vacuum's energy is perfectly even, how can you access a difference? How can you catch a wave that exists everywhere at once? You cannot harness wind without a breeze, nor draw water without a current. And the vacuum provides neither. It is like trying to sail on a perfectly calm sea that refuses to ripple. One of the most important limitations comes from the quiet laws of thermodynamics. These laws, expressed not through symbols here but through simple ideas, tell us that energy can only be extracted when there is a difference, a contrast between high and low, between warm and cold, or between motion and stillness. Energy machines need gradients. They need something to fall, something to slide downhill, something to flow. But zero-point energy is already at the lowest possible level allowed by the rules of quantum physics. There is no downhill from this point, no place for the vacuum's gentle tremble to sink further into stillness. Without that gradient, all the elegant mechanisms we use to extract energy from other sources simply cannot operate. Even effects like the Casimir force, the beautiful demonstration that the vacuum can push objects together, do not offer a loophole. The force arises not because you are drawing energy from the vacuum, but because you are comparing two regions of vacuum with different allowed vibrations. It is the difference that creates the push, not a flow of usable energy. If you try to set up a machine that moves indefinitely using Casimir forces, the universe gently resists. The moment you attempt to harvest the force repeatedly, you find that the system refuses to offer a net gain. Like a pendulum in a clock, the motion continues only as long as energy is supplied from outside. The vacuum does not give up fuel, it merely rearranges itself. Yet while extraction seems out of reach, manipulation is not, and this is where the story becomes beautifully subtle. If you cannot drain the vacuum, perhaps you can shape it. Engineers and physicists have begun creating nanoscale devices capable of altering how the vacuum quietly trembles. These devices are unimaginably small. Tiny cavities etched into metal or semiconductors, gaps narrower than bacteria, surfaces sculpted with patterns so delicate they resemble frost on a window pane. When objects are placed incredibly close together at these scales, the vacuum between them changes character. It shifts, ever so slightly, responding to geometry. By arranging surfaces in clever patterns, scientists can adjust the vacuum's local behavior. They can strengthen or weaken Casimir forces. They can create regions where the vacuum pushes instead of pulls. They can cause certain frequencies of the vacuum's soft vibrations to resonate differently, almost like tuning an instrument. This is not energy extraction, but it is control. And control, even in the smallest sense, is often the first step toward deeper understanding. One of the most promising directions involves metamaterials, engineered structures designed to influence waves, whether light waves, sound waves, or even the delicate ripples of the vacuum itself. These materials contain patterns repeated at tiny scales, patterns that change how fields behave inside and around them. When placed in a carefully designed environment, a metamaterial can make the vacuum tremble differently, guiding its subtle energy in ways that resemble the gentle shaping of wind through the sails of a ship. Scientists have also begun experimenting with nanostructured surfaces, arrangements of ridges, grooves, and pillars so small that they interact directly with the vacuum's faint vibrations. These structures do not generate energy, but they demonstrate that the vacuum is not indifferent. It responds. It softly bends to the shape of what surrounds it. This kind of engineering requires incredible precision. The objects must be aligned to atomic distances. Surfaces must be polished smoother than most mirrors, and the environment must be free from disturbances, heat, air currents, stray electromagnetic fields, all of which can overwhelm the delicate behaviors they hope to study. In these quiet laboratories, researchers work almost like watchmakers, crafting instruments that can coax the vacuum into revealing its subtle interactions. So where does this leave the dream of limitless energy? Perhaps not in the realm of extraction, but in the realm of inspiration. The vacuum may never provide fuel for our machines in the traditional sense, but its behavior may lead us to new principles of physics, new forms of materials, and new ways of interacting with fields and forces. The vacuum's uniformity and stability, once seen as obstacles, may become guides pointing toward more creative approaches. As we drift forward into the next part of our journey, the story will turn from energy to something even more intriguing. If the vacuum cannot easily give us power, might it instead shape the very forces we feel? Gravity, inertia, and the curvature of space itself? Perhaps zero-point energy influences far more than the motion of particles. Perhaps it touches the way the universe holds itself together, and for that, we'll need to explore ideas that lie at the edge of scientific imagination, where speculation must be carried gently, like a fragile lantern in the dark. There are moments in science when a question, whispered at the edges of understanding, feels almost too bold to voice, and yet it lingers, softly, persistently, like a thought that returns each time the room grows quiet. One such question is this: could the vacuum itself, with its gentle trembling and ever-present motion, play a role in shaping the very forces we experience every day? Not the exotic forces of distant galaxies or black holes, but the familiar ones: gravity, the pull that keeps your feet on the ground, and inertia, the subtle resistance you feel whenever you try to start moving or stop. These forces seem so ordinary, so woven into the rhythm of daily life, that it's easy to forget how mysterious they truly are. Inertia, for example, is something we have all felt. When you try to suddenly stand up from a chair, your body resists for a moment. When a car begins to move, you feel pulled backward. When it stops, you feel pulled forward. These sensations are so familiar that we often stop asking why they happen. Why does matter resist changes in motion? What gives it this quiet reluctance to be moved? For centuries, inertia has been described as a property of matter, a kind of built-in stubbornness that objects simply possess. But some physicists have wondered whether there might be a deeper explanation, something woven into the vacuum itself. One idea, developed by a group of researchers, imagines inertia not as a property of matter alone, but as a result of the way matter interacts with the vacuum's trembling fields. In this gentle picture, when you push on an object, you're not merely pushing against the object, you're pushing against the sea of zero-point fluctuations that surround and move through it. It is a little like running on a still day. Even when the air feels calm, your movement pushes against it, creating a subtle pressure that you can feel in your chest and your stride. The air may feel empty, but it is not empty at all. It resists your motion, and in doing so, it shapes your experience. In the speculative model inspired by this analogy, inertia arises because matter pushes against the vacuum's quiet hum whenever it tries to accelerate. The vacuum is not a substance in the ordinary sense. It does not drag on objects or slow them down. Instead, it behaves as a kind of elastic background, a field that reacts subtly when matter attempts to move differently than before. This reaction feels like resistance, not because the vacuum is heavy or sticky, but because its trembling fields gently oppose sudden changes. This idea has not been proven, and it remains one of many possible explanations, but it offers a poetic bridge between the small and the large. It suggests that the vacuum, though invisible and elusive, might help define how objects behave. In this view, every movement you make is accompanied by a silent partnership with the vacuum around you. Each step, each gesture, each moment of acceleration comes with a subtle whisper from the quantum world. Gravity, too, has been the subject of similar curiosity. Einstein showed that gravity is not a force in the traditional sense, but the shape of space itself. Objects move along the curves of space-time, drifting as naturally as marbles roll toward the lowest point of a bowl. But what determines the stiffness or softness of space-time? What sets its elasticity, its ability to bend? Some researchers have wondered whether the vacuum might play a role here as well. If zero-point energy is truly woven into the fabric of space, perhaps it influences how space curves in response to matter. In one speculative idea, the vacuum is imagined as a kind of medium whose underlying structure resists distortion. When matter gathers in one region, like a star forming in a cloud of gas, it bends the vacuum around it. The vacuum responds, not with friction or force, but with shape, and that shape is gravity. This idea does not replace Einstein's insight. Instead, it offers a possible explanation for why space behaves the way it does. Just as a trampoline stretches under weight because of the tension in its fabric, Spacetime might curve because of the tension held in the vacuum's underlying fields. These ideas remain unproven, of course. They sit at the edges of modern physics, where creativity and caution walk hand in hand. They are not claims, but invitations, ways of imagining how the universe might weave its laws together. One of the beautiful things about science is that it allows room for these possibilities. It does not ask us to believe them without evidence. It simply allows us to explore them gently, without rushing, as long as we remember that speculation must eventually bow to experiment. Still, even if the vacuum does not directly create inertia or shape gravity, the fact that we can imagine such a connection speaks volumes about how deeply zero-point energy is embedded in our theories. It is not a small detail that can be ignored. It is a quiet participant in the universe's story. Whether it shapes forces or simply coexists with them, it remains fundamental, a reminder that the simplest experiences, standing, walking, lifting your hands, may be rooted in something far more intricate than they appear. One way to picture this connection is to imagine the universe as a vast layered ocean. At the surface, waves roll in patterns we can see and feel. These waves are like the familiar forces, gravity, inertia, electromagnetism, moving across the world. But beneath the surface lies a deep undercurrent, calm but powerful, guiding the behaviour of the water above. Zero-point energy may be part of that undercurrent. It may not be visible, but its motion could help shape the contours of the surface world. Another image is that of a dancer moving across a stage. Each step, each turn, each lift is influenced not only by the dancer's strength, but by the floor beneath them, the way it gives slightly under pressure, the way it responds to weight. The vacuum could be something like that floor, an invisible support that shapes how matter moves, even if we do not see it directly. As we drift further into this story, we will explore even more daring possibilities. If the vacuum can shape forces like inertia and gravity, even slightly, what might happen if we could learn to shape the vacuum in return? Could we alter the curvature of space? Could we influence how objects move, not through force, but through the quiet architecture of reality itself? The answers are uncertain, but the wondering is worthwhile. Tonight we hold these possibilities softly, like delicate threads that may someday weave into new understanding. There is a certain magic in imagining the universe not as a static backdrop, but as something soft and alive, something that bends, stretches, twists, and perhaps even breathes. When we think of space in everyday life, we picture emptiness, the empty room when everyone leaves, the empty air between your hands, the empty silence of a night sky. But physics paints a more delicate portrait. Space is not simply the absence of things, it is a flexible fabric with its own quiet personality. And occasionally, when curiosity becomes brave enough, we ask whether this fabric could ever be shaped or influenced by the vacuum's subtle energy. It is here that we encounter some of the most imaginative, yet scientifically grounded ideas ever whispered about the nature of reality. One of the most intriguing concepts in this realm is something known in scientific literature as a warp geometry, though that phrase often brings to mind scenes from science fiction rather than physics. In its simplest form, it is the idea that instead of pushing a spaceship to extraordinary speeds, one might shape space itself. The idea is gentle in its core. Space can stretch, and space can contract. So what if one could ride those curves? Not by moving faster than light, but by letting space shift around you the way a river carries a boat. This concept grew from an equation, a mathematical oddity discovered by a physicist who wondered what would happen if space-time itself was sculpted into a bubble that contracted in front and expanded behind. The object inside the bubble would not move through space in the usual sense. Instead, space would carry it along. Within the bubble, the object could feel almost no motion at all. To the outside world, it might appear to move astonishingly fast. The intriguing part is that the idea doesn't violate the basic speed limit of the universe, because nothing inside the bubble moves faster than light, relative to its own little pocket of space. It is the space itself that shifts. But for this bubble of bending space-time to exist, it requires something that nature does not freely offer: regions where energy behaves in an unusual way. These regions are often described as having negative energy, though not in the sense of a numerical value falling below zero like a bank account going into debt. Instead, it refers to a gentle rearrangement of the vacuum, where the usual tremble of zero-point motion is suppressed in a particular pattern. Think of it like smoothing a wrinkle on a sheet by pulling in one direction while letting another part loosen. The sheet is still there, still part of the same fabric, but its shape changes in response to the tension. This idea of negative energy is not entirely fantasy. We see hints of it in small, controlled experiments. The Casimir effect, the quiet push between metal plates that we explored earlier, is sometimes described as creating a region with slightly less vacuum energy between the plates than outside them. It is, in a simplified sense, a tiny pocket where the vacuum's trembling is muted. But the effect is small, so faint that only delicate instruments can detect it, and only over the tiniest distances. To create something as dramatic as a warp bubble would require negative energy on a scale that dwarfs anything we can produce today. Not only that, but the arrangement would need to be precise, steady, and vast, like sculpting the surface of a lake so that a wave travels exactly the way you imagine. Another difficulty comes from the gentle but firm rules of quantum physics. Even if negative energy can appear in small quantities, nature seems to enforce limits on how long these pockets can last and how large they can grow. These rules are sometimes called quantum inequalities, though we need no equations here, only the idea that the universe protects its balance. Just as a stretched rubber band can only be pulled so far before it snaps back, regions of suppressed vacuum energy appear only in brief, localized bursts before returning to their usual state. This suggests that using them to shape spacetime in dramatic ways may be possible only for extremely tiny distances and extremely short times, far too fleeting for anything resembling a spacecraft to use. And yet there is something beautiful in the idea that these possibilities are not entirely forbidden, merely constrained. The universe is not saying no, but not like this. Not with the tools we have now, not with our current understanding. It allows the door to remain half open, inviting us to keep exploring. As we drift through these speculative ideas, it is important to hold them gently. They are not predictions. They are questions illuminated by curiosity. They ask whether the vacuum with its quiet trembling could be shaped into something more, whether space could be coaxed to bend in ways that reshape motion, distance, or even time. They do not claim that such engineering will be possible. Instead, they hint that the universe is more flexible than it first appears, and that our understanding of space is still in its early chapters. To imagine this flexibility, picture space as a vast sheet of fabric stretched across a frame. Normally it lies flat with only small curves where stars and planets sit. But imagine, just for a moment, that you could gently pinch the fabric above one point and pull upward, creating a small hill. And then imagine pressing softly around that hill, creating a valley on the other side. This is how the warp bubble concept imagines space-time, lifted in one region, lowered in another, forming a wave that moves across the fabric. The spacecraft rides inside the flat part of the wave, carried along by the motion of space-time itself. This is, of course, only a metaphor, and like all metaphors, it hides some of the difficulties. Space is not made of threads and fibres that can be pinched by hand, but the image helps us understand the essence of the idea, that motion might someday be guided not only by engines or fuel, but by geometry, by the quiet orchestration of the vacuum structure. These speculations remind us that the vacuum is not a passive emptiness. It is the medium through which light flows, the fabric in which particles appear and disappear, the canvas on which gravity paints its curves. And if zero-point energy is part of this fabric, then understanding it more deeply may one day lead to new ways of thinking about motion, stability, and even the shape of the universe. As we move onward, our attention will shift from these grand possibilities to something more grounded but no less fascinating. The prospect of shaping the vacuum itself, not to travel across the stars, but to create new forms of technology, new materials, and new ways of interacting with the hidden architecture of space. For now, let the idea rest softly in your mind. Space-time is not fixed. It moves, breathes, and bends, and somewhere within that malleability lies a mystery still waiting for us to uncover. There is a quiet charm in imagining the technologies of tomorrow, not as louder, brighter, or more forceful versions of what we have today, but as gentler ones, delicate instruments that work not by overpowering nature, but by listening closely to its rhythms. Over the past century, human inventions have grown steadily more refined. We learn to amplify faint signals, to manipulate light with precision, to control atoms one by one. And now, at the smallest scales of all, scientists are beginning to shape not just matter, but the vacuum around it. This emerging frontier, still in its infancy, hints at a future in which engineering may involve guiding the vacuum's subtle vibrations as naturally as we guide electricity through wires or light through fibre. To appreciate this possibility, imagine being in a quiet room with a single candle flickering on a table. The flame dances gently, shifting with each tiny current of air. Now imagine cupping your hands around the flame, not touching it, not smothering it, but shaping the air so that the flame steadies or leans in a particular direction. You're not changing the candle itself, you are guiding the environment around it. Quantum vacuum engineering is like this, but on a scale so small it lies beyond the reach of ordinary senses. By shaping the boundaries and surfaces around the vacuum, scientists can subtly guide the way it trembles. One of the earliest forms of this shaping comes from the Casimir effect we explored earlier. When two surfaces are placed extremely close together, they alter the vacuum's whispering fluctuations. The vacuum can vibrate more freely outside the gap than inside, creating a gentle push. This phenomenon was once seen as a curiosity, a theoretical oddity, but it has now become a cornerstone of vacuum engineering. If the vacuum responds to the geometry of its surroundings, then perhaps geometry can be used as a tool to tune the vacuum's tremble the way a musician tunes a violin string. Nanoengineering has become the key to unlocking this possibility. At incredibly small scales measured in billionths of a meter, materials can be carved, layered, and patterned in ways that would have seemed impossible only decades ago. These tiny structures behave not simply as surfaces, but as landscapes that guide the vacuum's energy. A surface etched with ridges might amplify certain vacuum modes while muting others. A thin cavity, so narrow that only a few molecules could pass through it, could act like a resonant chamber for the vacuum's faint motion. Even the choice of material, whether metal, graphene, or a carefully engineered composite, can influence how the vacuum responds. Graphene in particular has become a star in this field. Only one atom thick, it is both incredibly strong and astonishingly thin, making it ideal for manipulating minute forces. Scientists have discovered that graphene sheets can respond to tiny changes in vacuum pressure, bending or vibrating in ways that reveal how the vacuum shifts. In this sense, graphene behaves like a drumhead stretched tightly across the smallest possible frame, sensitive to vibrations no ordinary instrument could detect. Experiments using graphene have shown that the vacuum's tremble is not just a theoretical idea, but a tangible presence that interacts with matter. Another emerging tool in vacuum engineering is the metamaterial, a structure made from repeating patterns so small that they influence waves in unusual ways. Metamaterials were first developed to guide light, bending it around objects in ways that can create surprising effects. Some metamaterials can even make objects appear invisible by redirecting light smoothly around them. But the same principles can be extended to the vacuum itself. At very small scales, a metamaterial can shape how electromagnetic fields behave, and because the vacuum's fluctuations involve these fields, the metamaterial can indirectly shape the vacuum's tremor. To visualize this, imagine placing small stones in a shallow stream. The water flows around them, forming gentle swirls and eddies. If you arrange the stones carefully, spacing them evenly, or shaping them into patterns, you can create beautiful, predictable currents. Metamaterials do something similar with fields. They create patterns that guide how the vacuum's quiet motions ripple through space. The result is not a change in the substance of the vacuum, but a change in the way the vacuum expresses itself. One of the most delicate forms of vacuum engineering involves tiny cavities known as optical or microwave resonators. These are small chambers that trap certain wavelengths of light while excluding others. When such a cavity is refined to the level of atoms, the vacuum inside behaves differently. The fluctuations become structured, organized by the cavity's shape. Scientists have observed that the vacuum inside these resonators can influence the behavior of atoms placed within them, causing them to emit or absorb light in subtly altered ways. This is a quiet reminder that the vacuum is not passive, but responsive. In the distant future, we may learn to shape the vacuum deliberately, the way an artist shapes clay, not to extract energy from it, but to use its structure to create new materials, new forces, or new states of matter. Imagine devices that reduce friction, not through lubrication, but by guiding the vacuum so that its fluctuations gently cushion moving parts. Imagine sensors so delicate that they listen to the vacuum's faint tremble to detect gravitational waves or distant cosmic signals. Imagine materials that remain stable in extreme conditions because their structure harmonizes with the vacuum around them. Such ideas may seem bold, but they're grounded in the quiet reality that the vacuum is not empty. It has structure, personality, and a responsiveness that invites exploration. As quantum vacuum engineering grows, it will likely move slowly, one delicate breakthrough at a time, but it has already begun in tiny laboratories with carefully polished surfaces and precisely etched patterns. In these places, the vacuum is no longer a background, it is a collaborator. This future discipline, gentle in its methods and profound in its implications, offers a different view of technological progress. Instead of harnessing greater force, it invites us to listen more closely, to work with the faintest signals nature provides. And as we drift toward the next part of our journey, the story will widen again, from technology to humanity, from what we can shape to how we choose to shape it. For the vacuum is not just a playground for physics, it is a reminder of how much potential lies hidden beneath the quietest parts of the universe. There is something deeply comforting about imagining a world where the constant hum of worry about energy simply fades into the background. Today, much of our global story revolves around fuel. how to find it, how to store it, how to distribute it, and how to use it without harming the planet that sustains us. Energy is the quiet engine behind every light, every screen, every hospital, and every city. It shapes economies, influences politics, and often determines the well-being of entire communities. Yet when we look at the vacuum, with its soft trembling and nearly limitless presence, we cannot help but wonder what life might feel like if energy were no longer a resource to struggle over, but something as natural and effortless as sunlight. Even if zero-point energy itself never becomes directly usable fuel, the ideas surrounding it, the technologies and insights born from studying the vacuum, might someday lead humanity into an age where energy scarcity feels like a relic of a distant past. To imagine such a world is not to predict it, but simply to explore how life might change if energy in all its forms were abundant, clean, and everywhere. Begin by picturing a city at night, its streets glowing softly, not with the harsh glare of overworked power plants, but with a gentler, steadier light. The buildings hum quietly, not because they are consuming immense power, but because they require so little. Advances in materials, perhaps inspired by vacuum engineering, could make electronics orders of magnitude more efficient, reducing waste until energy becomes something hardly noticed, like the warmth of a room or the breath of wind across a field. In such a world, homes might not need power lines stretching from place to place. Small, compact devices, using highly efficient quantum technologies, not vacuum extraction, could generate or store energy at the point of use. Rooftops might hold silent panels tuned not only to sunlight, but to a broad spectrum of gentle environmental signals. Floors might capture the soft vibrations of footsteps. Windows could shift their transparency to harvest or release heat precisely when needed. The idea is not that every object becomes a generator, but that energy becomes so easily gathered and managed that the concept of running out begins to lose its meaning. Transportation, too, might feel different. Imagine vehicles that glide more quietly, powered not by combustion or even by large heavy batteries, but by smaller devices that draw from subtle physical processes, clean, dependable, and nearly maintenance-free. Trains could run on tracks that use ultra-low friction materials developed through an understanding of the vacuum's delicate structure. Aircraft might rely on engines that consume minimal fuel, their efficiency shaped by technologies born from quantum insights. And for journeys beyond Earth, spacecraft might use propulsion systems that nudge gently against natural fields, gliding through space with more grace and less force. On the global scale, such a transformation would ripple through every aspect of society. If energy becomes inexpensive and decentralized, nations no longer depend on distant fuel sources. Regions once vulnerable to scarcity would gain stability. The cost of lighting a home, purifying water, powering a school, or heating a hospital could approach zero. This shift would not erase challenges from the world, but it could soften some of the most persistent pressures, giving communities room to grow, breathe, and imagine new futures. The geopolitical landscape might change in subtle, gentle ways. Without the intense competition for fuel, countries could redirect their efforts from securing resources to building knowledge, improving health, and deepening cooperation. Conflicts rooted in scarcity might lose their urgency. Economies might reorganize around creativity, engineering, and stewardship rather than extraction. The global narrative might shift from one of competition over limited energy to one of collaboration around abundant possibilities. The environment would feel the difference too. If clean, plentiful power is available everywhere, forests could recover where they were once cut for fuel. Rivers could flow more freely, unburdened by dams needed solely for electricity. The air in cities might become clearer, gentler on the lungs. Even the oceans could slowly heal as the pressures of pollution ease. With energy no longer tied to the burning of fuels, humanity might find itself living more lightly on the planet, not through strict discipline, but through natural technological evolution. But perhaps the most beautiful change would happen within our daily lives. Imagine waking up in a home warmed not by loud units, but by quiet systems that respond seamlessly to your presence. Imagine never worrying about whether a storm will wipe out your electricity, because your sources are so varied and resilient. Imagine hospitals that never fear sudden shortages, farms that control climate within greenhouses, using almost no additional power, and schools where every child has access to technology, unrestricted by cost. Energy would shift from being a concern to being a foundation, quiet, reliable, and taken for granted, the way we take sunlight for granted. This would not make life perfect, nor remove every challenge, but it would create space for humanity to breathe more easily, to explore with less fear, and to focus on the things that matter most: health, curiosity, connection, and care. And yet, even in this hopeful vision, a gentle reminder remains. Abundance alone does not guarantee wisdom. If energy becomes effortless, the responsibility to use it well becomes even more important. Technological power, like any form of power, asks for humility. A world without scarcity invites questions. How do we share? How do we protect? How do we ensure that abundance benefits everyone, not only a few? These questions lead naturally into the next part of our journey, a reflection on the responsibility that comes with understanding reality at its deepest levels. If the vacuum's quiet hum inspires new technologies and new forms of abundance, then we must learn to shape those possibilities with care, like an artist approaching a blank canvas with both excitement and respect. For now, let this vision of a peaceful, abundant world settle softly in the mind. It is not a prediction. It is a dream, a gentle exploration of what might one day unfold when humanity listens closely to the quietest parts of the universe. There's a special kind of quiet that settles in when we begin to talk about responsibility, not the heavy kind that weighs on the shoulders, but a gentler, reflective kind, the kind that comes when you realize you're standing close to something ancient and delicate. If humanity ever reaches a point where we can shape the vacuum's subtle patterns, or guide the trembling of quantum fields the way we guide the flow of electricity today, then we will also find ourselves holding a new kind of responsibility. Not the responsibility of managing a resource or balancing supply and demand, but something far deeper. The responsibility of touching the canvas on which the entire universe is painted. To understand this responsibility, imagine sitting before a vast mural. It stretches across the walls of a cathedral-like hall, filled with colours so soft they seem alive, shapes interwoven with meaning, patterns that shift as the light moves. This mural represents the structure of the universe, the quiet tension of space-time, the trembling of the vacuum, the rules that let atoms form and stars shine. For all of human history, we have lived within this mural, interpreting its shapes and admiring its complexity, but never touching it directly. Slowly, over centuries, we learn to trace some of its layers, to understand small parts of its design. But the idea of altering any part of it, of changing the strokes themselves, was beyond imagination. Yet if our journey of understanding continues, the day may come when we can influence the vacuum in ways deeper than geometry alone. Already, from the smallest Casimir forces to the speculative notions of bending space, we see hints that the vacuum is not untouchable. It responds, however gently, to the shapes we impose, and the more we learn, the more that quiet mural of reality begins to look less like a painting and more like a living tapestry, something woven, something responsive, something that invites both awe and caution. This is where responsibility enters the story, because whenever humans discover a new pattern, a new principle, or a new kind of influence, we tend to reach for it. We shape tools, we build machines, we dream of what might be possible. But with the vacuum, the stakes feel different. The vacuum is not just another material, not another energy field or substance. It is the foundation upon which all matter and energy rest. To shape it is not like reshaping metal or carving wood. It is more like nudging the frame of the world itself. One gentle analogy is to imagine tuning a musical instrument while the concert is already underway. The universe is the concert, filled with harmonies and rhythms that have played for billions of years. Zero-point energy is like the faint vibration of the strings beneath the music. If we ever learn to tune those strings directly, even slightly, we would be adjusting an instrument that all of existence relies on. Perhaps we could enhance certain notes, soften others, or create new harmonies. But even the smallest adjustment must be made with care, because the music is not ours alone. We are participants, not conductors. Ethical questions begin to unfold from this image. Who decides how the vacuum should be shaped? Who has the wisdom to guide such changes? Should the ability to influence the foundations of physics belong to all of humanity, or to a few? Would access be restricted, shared, or monitored? How do we ensure that such knowledge is not used carelessly, or with intentions that overlook the interconnectedness of all things? These are not questions with simple answers, and in truth, they are not questions for today or even tomorrow. The ability to manipulate the vacuum in profound ways remains far beyond our reach. But the ethical reflections begin now, in the space between curiosity and capability. They are part of the humility that comes from learning, not the humility of smallness, but the humility of honor. The honor of being part of a universe that invites us to explore, yet reminds us that exploration must be balanced with care. Another way to understand this responsibility is to imagine ourselves as guests in an ancient house. The structure is older than we can fathom. Its beams hold stories from long before our arrival. Some rooms we understand well, others are still mysteries. We live within this house, sheltered by its architecture, warmed by its light, nourished by the cycles it sustains. If we ever gain the ability to alter its supporting beams, to strengthen one, weaken another, or shift the foundation, we must do so with deep respect. A careless change could ripple through the entire structure. In the context of zero-point energy and vacuum engineering, the beams are the laws of physics, the quiet rules that shape motion, light, gravity, and matter. These laws have held the universe together for billions of years. They have guided the birth of stars, the formation of galaxies, the chemistry of life, and the unfolding of consciousness. They are not rigid commandments carved into stone. They are patterns woven into the vacuum's trembling. If we ever learn to modify those patterns intentionally, we would be touching the framework on which everything else depends. Such thoughts can feel intimidating, even overwhelming. But there is comfort in them as well. The universe has always allowed us to learn at a gentle pace. Every step we take in understanding is matched by a reminder to listen carefully. And the more we listen, the more we realize how delicate and beautiful the foundations truly are. This reflection is not meant to discourage curiosity. On the contrary, curiosity is the spark that brought us here, to the edge of understanding the vacuum, the quiet hum beneath all existence. Curiosity is what lifts us generation after generation from darkness into deeper clarity. But curiosity without humility can become reckless, while curiosity balanced with reflection can become wisdom. As we drift toward the closing part of our journey, let this idea settle softly. Understanding the vacuum is not just an intellectual accomplishment, it is an invitation to responsibility, a reminder that the universe is not merely a collection of parts to be manipulated, but a living harmony in which we participate. And if we ever learn to shape its deepest layers, we must do so with reverence, knowing that we're touching something older than stars, more subtle than light, and more fundamental than the matter that forms our bodies. With that thought in mind, we move gently toward the final chapter, not with conclusions, but with a sense of quiet presence. The vacuum's hum continues beneath everything, and in that hum we find both mystery and meaning. If you return your mind just for a moment to the very beginning of our journey, back to that soft idea that the universe is never truly still, you may feel something familiar unfolding again. Throughout these sessions, we've drifted through trembling atoms, shimmering fields, the weight of empty space, the dream of boundless energy, and the delicate responsibility that comes with understanding the foundations of reality. And now, as we near the end, the path gently circles back to where it began. Because beneath all the theories and possibilities, beneath the technology and the imagination, there remains one simple truth. The universe hums, softly, endlessly, and everywhere. This hum is not a sound in the usual sense. You cannot hear it with your ears. It does not echo across valleys or ripple across lakes. Instead, it is a presence, a quiet trembling in every corner of space, from the smallest gap between particles to the vast distance between galaxies. It is the heartbeat of the vacuum, the faint signature of zero-point energy. Even in the deepest silence, even in the emptiest void, the universe is alive with motion. To feel the significance of this hum, imagine sitting outside on a calm night. The world feels still, suspended beneath the dark sky. Yet if you listen closely, not with your ears, but with your awareness, you begin to sense that the stillness is only one layer of the experience. Beneath the quiet, insects move through grass, distant leaves shift in the breeze, and the air itself vibrates with life too subtle to perceive fully. The vacuum's whisper is like this, ever present, supporting everything, whether we notice it or not. Throughout our journey, we've explored how this whisper shapes the familiar world, how it stabilizes atoms, influences molecules, and forms the foundation for technologies that quietly guide our days. We've drifted into the cosmic scale, where this same whisper stretches the universe gently outward. We've imagined the far future, where humans might learn to sculpt the vacuum's delicate patterns. And we've reflected on the responsibility that accompanies such wonder. Yet the beauty of this story is that it doesn't end with answers. It ends with presence. The whisper beneath everything is a reminder that reality is layered. What appears empty is full. What seems silent vibrates. What we call nothing is a reservoir of subtle activity, the first and last breath of existence. Even when life feels still or uncertain, the universe continues its gentle motion. There is something deeply comforting in knowing that beneath every moment, joy, difficulty, rest, or confusion, there is a quiet foundation that never falters. Another way to picture this whisper is to imagine a lighthouse in fog. The beam sweeps softly across the water, sometimes hidden, sometimes faintly visible, but always there. The vacuum's hum is like that steady light, a constant presence behind the shifting patterns of the world. It does not demand attention. It simply exists, providing the baseline from which all things arise. If you look inward, you might also recognize that you too are part of this trembling fabric. Your body, your thoughts, your breath. Each is built from atoms held together by the same quiet rules that shape stars. In a sense, you're not separate from the vacuum. You're made of it. You're woven into the same tapestry of trembling fields. When your heart beats, it resonates with the same laws that govern galaxies. When you breathe, you're participating in the universe's quiet motion. You belong to the same whisper, the same gentle undercurrent that has existed since the earliest moments of time. This connection can bring a sense of peace. It reminds us that even when we feel alone or adrift, we are held by something vast and ancient. The vacuum does not choose sides or divide, it simply is. And in its quiet steadiness, there's a kind of comfort that asks nothing from us except to notice, to rest, to let ourselves drift for a moment in the awareness that stillness is never empty. One of the most soothing thoughts in physics is the realization that nothingness is full of possibility. The vacuum is not a void, but a canvas, a place where particles can appear, where fields can dance, where space can curve, and where time itself flows. It is a reminder that emptiness is not the absence of meaning, but the beginning of it. Many cultures throughout history have described the world as arising from a quiet, fertile stillness. Modern physics, in its own way, echoes that sentiment. As our journey comes to its quiet close, consider the way this whisper threads through everything you've heard. It is the hum that keeps matter from collapsing, the tremor that shapes forces, the tension that stretches the universe, the subtlety that hints at untold possibilities. And it is also the softness that accompanies you now, the feeling that the night is never truly silent, that the universe is gently alive even when you close your eyes. This is one of the gifts of exploring physics in a calm, unhurried way. Instead of rushing toward answers, you begin to sense the wonder in the foundations. The universe becomes less a collection of equations and more a living presence, subtle, beautiful, and endlessly patient. And in that presence, you might find that the quiet around you feels a little deeper, a little warmer, a little more connected. Before we part, let yourself rest in the image of the vacuum's faint hum, the whisper beneath everything. It is the same whisper that supported the earlier stars, the same whisper that moves through your breath, the same whisper that will continue long after our brief stories have passed. Time softens, the world grows quiet, and the hum of existence becomes a kind of lullaby, steady, ancient, and always there. You are part of that whisper. You always have been.